Large language models can feel like a magical tool when you're using them through a polished chat interface. But when you actually run one for yourself, that illusion disappears quickly. In this video, I'm going to be explaining how transformers work on a systems level and why I built a minimal LLM interface to show the costs and limitations of a base LLM. In this image here, we have an example of how embeddings work. This is what the core of language models are based off of. Instead of taking words as symbols, models will represent them as a vector in a high-dimensional space. That means that these aren't stored explicitly, but they're encoded with distance. So you can see here that king and man are kind of close, while king and queen are also semi-close. And there's all these different words that are related on this plot. And we can also see here that there's a different part of how words are embedded within these vectors. And they use a contextual embedding, where some of these words might map to different vectors depending on how they are used. So we can see that this bank, depending on whether we're talking about a river bank or if we're talking about the money type of bank, they could behave differently. So this shift from symbols to geometry is what caused large-scale language models and understanding to be possible. We can see here that transformers are really what introduced attention to models. This allowed every token to directly reference every other token. This is sort of how it gets that context that we were talking about in our embeddings. It means that the model doesn't directly process text strictly from the way that it's inputted. It goes and reasons over the relationship of those different words. So we've got our normal input here, which is the cat down. Normally, a human would look at this and not necessarily know what it means. The LLM also wouldn't necessarily know what it means right off the bat. And we can see that there's all these different, essentially, arrows all over the place. This is kind of intentionally messy, but every single word not only has reference to itself, but reference to the words before it, behind it, reference to the entirety of every possible way that these might be used together is essentially the idea. So it's caused transformers to ultimately be the main used model, whether that be for image generators, audio systems, and video generation. But the problem is with this is we've got a lot of extremely expensive and poorly scaled attention. Just because we've got all of these words referencing each other, they may not need to reference each other. They may not be that important to each other. That kind of gets into one of the important things to know about the model and how these models work, where they're choosing a top P value and they're assigning what the words in the input should be weighted as to importance. So the model might go and put the as a zero point 0.01 because maybe it's not that important, and cat might be zero point 0.9, and down is only the remaining amount between the and cat adding to 1. So one of the things that happens with LLMs is in our reasoning is not something that like we implicitly program into the model. We don't go and tell the model, well, when you see these words with these embeddings, then you can assume this. The model naturally learns those things. So as that model grows larger and larger and it sees more data, you get that reasoning emerging. We can see that kind of in this graph here, that as the model is growing in size, we kind of get to a point where it's got some reasoning. We get to a point where it can do that pattern matching, and it continues and continues and continues with scale up to a certain point. We can kind of see that it does start to plateau, but just because it's plateauing doesn't mean that we don't have other tricks that we can use. We can see that in our training behavior, we've got different ways to shape that scale. So our pre-training teaches that model about the language and the world that it's in. So we can think of a model that's specifically trained for dealing with customer service. That might answer questions, it might provide solutions in a different way than a model that is specifically designed for teaching math to a student. They've got different use cases. So we do some preference optimization for this. We do some feedback tuning. And what this pre-training does is it doesn't go and add any new knowledge to the model, but it shapes how that model responds. We can think of things like chain of thought or tree of thought, program of thought. Those aren't making the model smarter. They're changing how the interface we use to the model is extracting reasoning. So this is where agent-like behavior starts to appear as we've pre-trained, post-trained, shaped, scaled the model. That's when the model starts to have reason. It starts to act, it has evaluation, and it can adapt. But none of those things really matter if you can't reliably run the model in the first place. So what I did is I started building a baseline LLM inference model. And so this is very bare bones. There's no evaluation even in place currently. This is just pure raw model. And so we can see what it's got is there's a fast API output to chat. And what this does is it has the chat come in and then it goes and sends it to a generator. This generator takes our model and it feeds the model with, how many tokens that it should output, the temperature that it should respond in, and then the top P value. As we discussed, that top P is sort of the giving the model its ability to weight the words in the sentence that we give it. And then when we return, we just log all of the stuff from the model. So we can see down here in our terminal that I have already run a example, and I ran this ahead of time because we can already see that our latency is rather large. This is one of the issues with this is the latency just out of the bat because the model spits out so much and it's not concise or to the point, and it literally will just go and use up those max tokens. It will just go and say, I have 160, I'm going to use 160. I have 1,000, I'm going to use 1,000. It doesn't care. It's not going to try to answer either the question that's asked or do the task that is specifically asked. It just gives. So I intentionally made it this way so that we can see these problems firsthand. And what this really shows is this is just the base Phi 2 model from Microsoft. And we can already see some of the problems of scale and the cost in order to run this model efficiently. Trimming down 60-ish thousand milliseconds of latency is not a necessarily simple task to do, but it's something that will require a lot of either pre-training and post-training in order to really scale it down and have it be concise in the way that it gives answers, or it would be something that you would have to start parallelizing and making it have access to more resources in order to do its compute. This is that same thing that we've talked about before, where that attention and embeddings and the size of the model starts to go and causes a lot of cost. So what we can see here is on our back end, we see that I sent this prompt just to say hello, right? And it's got a low temperature, so it's going to be trying to return truthfully as close as possible to this say hello. And our top P, if I were to make this larger, we would see a slightly different reaction possibly, as well as if I made this slightly smaller, we would see a slightly different reaction. But having it at about one, because it can be between one and two, is a fine place just to start your playing with the tool. So I just asked for it to say hello, right? What would we think that this model should do is just return hello. That's it, right? But we can see here in our response that we get a literally what I said, and it decided world. I didn't ask for world. I didn't ask for a tutor. I didn't ask for it to do a function and returning something, and now it's doing a student thing here where it's like role playing a tutor and a student, and it's talking about how to basically create a function in Python to print hello world. That's not at all what I asked this model to do, but that's the norm of how this works. That's what we can expect from a model that doesn't have a ton of pre-training specifically for how I want that model to work, or post-training where I'm doing that human feedback to this model to give it what it should be giving back. So this really shows a limitation that models have in and of themselves. Without any extra evaluation or training, it the model itself is very limited in what it can do. There's also a lot of issues you would run into without using Docker. And just getting this project set up, I ran into a lot of Python version compatibility issues between Torch and some of these different models. You'll run into different issues like model architecture differences. Originally, I tried using a non-encoder and decoder model, and the model would just output the new line characters. It would do \n for anything that I gave it. I tried prompting it like in a question answer format, and it would just return question answer and then a bunch of the new line characters again. So depending on how you set up your architecture and you're using the model, it does have an impact on that model's base performance as well. You can see the latency. Again, we've mentioned that the latency is very high for this model. The Phi model is rather large in comparison to some of the smaller models that I tried to use from Hugging Face, but I couldn't even get a reasonable output to show when using those smaller outputs without any sort of pre or post training. And we can see that our token cost in order to give these answers from the model. All of these things we know that tokens in models are one of the bigger limitations that we're facing right now. And some of the frontier models, like from OpenAI and Anthropic, are starting to address some of these token issues. When you're running this locally, you get to learn some of those tricks, and I'll go over those later as I continue to build over this project of how we can make these tokens more efficient. You can see that from our project, all I asked was for two tokens. Those are the two words that I asked, say hello, and it decided that 113 was the correct amount of tokens to use. That's just a true inefficiency of these models. And it shows how we can have a infrastructure problem first before these models are an intelligence problem. We've got the infrastructure that we have to deal with of getting the latency reduced, making sure that we're able to have the model completely pre and post trained before we can actually get some of that intelligence from these models. So in my next videos, I'll be going over adding in some evaluation. I'll be going over more in depth on how to pre-train, post-train these, how to make these models really effective and actually have some value to you. So I hope this was helpful. I hope you learned about embeddings, learned some of the key features of transformers like attention. Know that scaling does change your behavior, that your reasoning emerges from scaling. Pre and post training can shape your preferences to the model, and the inference can expose real constraints. Keep this in mind as you're working on any sort of transformer projects. And if you need any help, I am available for answering any questions to work on your own projects. And you're more than welcome to contribute to this project. And I will have that project link in the description. Thanks for watching.